Yellow, everyone. And welcome to the second part of the node graph to native code stream. Let's put the music down maybe just a tad. Like so. And we can get started here. So this stream is actually very early in the day for me. Let's get the visual out of the way. So a couple of days ago I streamed a little bit of myself working on this latest endeavor that I've set out on in the development of Traction Point. So we have these node graphs that we create particle effects using. So here, for example, is one such particle effect, just a very simple little thing. Generates particles around the world origin here, because this is the preview. But anyway, assigns a random velocity and then updates the color, and all of that is done through this piece of node graph here. And so the new thing that that I've been working on lately is the fact that you can now generate native code out of this stuff. And so here you can see the generated code for this particle effect. It's pretty long actually, it's like 700 lines just for this simple effect, but that's just because like we have a lot of this sort of thing. The code can be perhaps made a bit more compact in the future. I'm just trying to make like the most basic thing that I can do currently. And so we have a lot of lists here that take up a lot of rows. But anyway, here you can see the individual nodes doing their thing. So we have some lerp vectors, we have some remap floats, we have some color vectors, all of the stuff here. And last time I was actually trying to get this thing visible on the screen, and I couldn't quite get there because it was considerably more complex than I had originally thought. That was a pretty popular stream though. Not huge, but it got a fair bit of views, and it got a fair bit of views sort of after the fact as well. And so I figured, okay, it's 2 days later, I made significant progress on this thing, so let's do a follow-up. So that would be this one. And already in the previous part we could see the thing here. This is because this preview here is running the particle effect in the interpreter, so the old mode, the old way that we actually are running these things already, and have been for like a couple of years already in the game engine. But I found out that the performance isn't particularly good, right, with that. And so this effort of actually converting these things to native code directly from the editor and then having the game engine render them, just running the node graphs as native code, is hopefully going to be much faster. Partly because I can just immediately, like, I can eliminate huge parts of the node graph like this, things that have been kind of slow in the past. And so I haven't quite gotten there yet. I haven't done any profiling on this, but I have actually been able to run this particle system now in the actual game engine. So let's take a look what we have. If we go to, here we go. So this is the game code, and I had a handy little, I think it was client player controller. Yes, here we go. So because he's commented out stuff here, because hacked this thing basically. Just to play this thing, when you actually press the debug the pause button, it will actually load the Merlin effect and then play it, create an instance and auto start it. So this will essentially create the effect in the world and play it immediately, and it will appear at the world origin because we're not actually setting any transforms or anything on it, right? So what would that look like? Well, if we can maybe shut this down. Let's go into the game and see what we have. A little bit of coffee. Right, so if I now press P, let's actually fly here. I know the world origin is somewhere here under the terrain. Let's press P, and boom, you can see. Here's our polygon system. Now this is not something particularly new or noteworthy. It's a bit dark because it's like sitting under the terrain, so we have the sunlight is blocked by the terrain and all of that. But yeah, this is not particularly noteworthy. We've been able to do this for very, very long. Of course, the new thing here is the fact that this is actually running as native code now, and we can verify that by opening up the code for those particle systems. So this was the color test, and here we can probably see some color nodes. So I don't have the pipeline set up yet where I could actually have these things get packaged automatically. Instead, what I do is I copy paste the code out of the particle editor, the generated code, and I paste it into this thing. And then when we build this thing, let's make sure this actually builds. It does not. Oh, okay. It's because I removed this business from here. Okay, let's make a small hack here. I'm just gonna comment this thing out from all over the place. This is the next thing that we're gonna be looking at today, and so I just basically cleared the slate there so that we don't have any old crap lying around. Yeah, that's not what we want to do. I only wanna comment out the first one, so let's just do it by hand. So we have to basically just have the system ignore this node graph number 2, which is of course the third node graph, 0, 1, and 2. 0, 1, and 2, we have the code gen test, which was the very basic first thing, which didn't even show any particle systems. Then we have the color test, which we just looked at, and then we have the cartoon smoke continuous. This is the dust effect that we're gonna start looking at today. That's one of the actual reasons why I want to make this thing faster, right? So, if we go and have a look here in the color test, we have this color vector node, and here we have the colors just straight up as 4-dimensional vectors, 4 components. So if we make like one of these, let's see, which one is this? This is kind of red, and this is kind of bluish. So of course the effect goes from being red to being blue. So let's just make this be green instead. Like this. That should be like 0. So it's like RGB and then alpha, right? So now if we actually build this thing like so, and then we go into the game again, and we press P to play that thing, we should be able to see that. Look at that. Now we have green to blue instead of red to blue, which just shows that yes, this is indeed running off the native code that we've generated in the editor. So that's pretty cool. So the effect that I wanted to try to get working today is this thing here. This is a somewhat placeholdery thing still, right? This dust effect that is spawned off the car. And this is one of the things that are actually like a little bit of problematic from a performance perspective, because you can actually have quite a few of these instances running even with just one vehicle. Like if you have some air time, like here for example, just like jump around like this. Obviously there should be some brakes in that effect. It shouldn't like follow you into the air. That makes sense. And so we actually like start new instances of that thing quite a few times actually during one of these like runs. So you can have something like 10 or 20 instances running, because of course there's one for each wheel. And if you just get airtime once, then you already have like 8 of them. But it can quickly escalate out of that. And some of the vehicles have like 6 or 8 wheels. So we need it to be fast. And this effect I haven't gotten working yet. I don't see any reason why it wouldn't work. It just needs a little bit more, well, work. So let's try to make that happen today. And then we can do some profiling, which is the whole reason I want to do this native code generation thing, is just to get these things to be very, very fast. So that should be fun. And we can open up this particle effect in the editor. If we go here and we open up this thing which is called material effects. This cartoon smoke continuous. It looks like this. It's a bit more complicated than the previous one. Should also be able to preview it here. You can see it looks kind of meh in the preview. It kind of just requires you that you actually move it around for it to look good. But anyway, it is this thing, and you can see that we actually can generate the code for this thing already. The problem is that we don't have all of the nodes implemented yet. So this is actually like, this is starting to become quite large. This is 1,500 lines already, especially with this like verbose mode, which just prints some like comments and things into the code, right? In particular, we have the curve node. So you can see here that we actually have a curve here. This guy, it's a very ugly curve. Oh, what's the cursor? The cursor look like that? That's strange. Huh. That's very weird. Cursor has this like white box around it. I don't know what that's about. Is that maybe something to do with like streaming? I don't know. Interesting. Anyway, we have a curve here. The curve is node 13. So we search for node 13. Here we go. So this guy. Because you get result. So we actually have a function here that we can call to get the result out of this, but it just returns 0. So we're gonna have to actually implement this guy and make sure it actually returns. So the way this works is that you supply it with the x coordinate. This cursor is really distracting me here. I don't know what is going on with this thing. Yeah, I should probably look at that off stream at some point. But anyway, you give it this axis, the value of this axis, which is the x-axis, and it gives you out like the y-axis. So it starts at 0 and it returns 0, and then when it progresses to the right, you get sort of like this kind of like growing and then shrinking. And we can see that we actually plug it into the particle scale eventually. So we're gonna have to do something about that, about the curve node not being implemented. And so that would be probably our first order of business here. And I was thinking maybe we should try that out actually with that other. Since we have this nice and already plugged into the game. So if we make a change here, let's play this guy. This is something that's like arguably more easy to actually see here in the editor. So let's just put a curve here into this guy. Let's drag a curve in, and we need to maybe adjust the scale of the particles. So let's plug this in, plug that there. Oh, come on. And then we get the scale from there, and we can drive it from 0 to 1, so that would be like normalized age of the particle. And then we just I'm gonna shut the game down here. We have some game sound effects in the background. Right, so we need to add some points here. Let's add one at 0, 0, 0 and 0. And then we can do at 1, which is like as high as the value is gonna go now because we're using the normalized age. It goes from 0 to 1. Let's make it 3. So what this should mean now, and we should immediately be able to see it here in the preview. If we click this, look at that. Now they're growing. Isn't that cool? Isn't that cool? And maybe to make it a bit more interesting, we can make it. Maybe make it. Like a smooth thing, or maybe like an exponential curve, something like this, right? So now they're sort of like they're starting off really, really small. We can see that the curve is kind of being evaluated correctly. You might be wondering, okay, we can actually see the thing here. How is that possible if it's not implemented? Well, again, this preview here is using the interpreted version of the node graph, which we don't want to use ideally in the game. We want to use the native one. Let's turn the grid off here. You see some of those really small guys just like flying around all over the place in the center there, and then slowing down, and actually maybe they aren't slowing down. I don't think they're slowing down. They just kind of look like they're slowing down because when their size gets bigger, it kind of looks like they're slowing down, but it's not, because you can see like after this update particle, we're not actually setting the velocity, we're just setting it in between emit and update. This is where you do like the initialization of your particles, and then after the update, this is where you do the actual update. Anyway, so this is cool. We should try and see if we can make this happen with the native ones, right? If we can do that, then I think we basically have everything we need to run the dust particle, the particle systems that trail after the vehicles in native mode. And if we can do that, then I will be a happy boy. So, let's try to make that happen. I'm gonna save this, just so we don't lose this thing. And again, we can see the code for this. There should be a curve node here somewhere. We can even find it here. It should be number 16. But if we just look for curve, you can see, yes, here it is, node 16. So even though it kind of works here, it outputs or generates this stub of a thing here, which we can't have. We need to actually evaluate the curve somehow. So how would we do that? Where do we even put the curve value, the curve data? You might ask. And my thinking is that we're just gonna put it straight into this struct here. No biggie. It's not gonna be very big. So we're just gonna quite simply hard code it into the thing. Let's go and have a look here. Find the effect file, Merlin effect testing, color test. So this is the change that we made. Let's open that in Sublime. You should be able to find some like tangents or something. Tangent in, tangent out. Yeah, here we go. Okay, excellent. So here's the curve node that we added. Bloop. It is ID 16, as you can see, which is the correct ID for it. The curve data is quite simply here. I don't know what post loop and pre-loop are. Something strange, but the points that we have is here and here. So we have x0, y0, x1 and y3. And that of course matches this 0, 0, 1 and 3. So that's fine. And then we have the tangents, tangent in, tangent out. So the first one has a tangent out, the second one has a tangent in. That makes sense. If we move this guy here, and then we add, maybe we can add one more point here. Put that on at 1 and 0, and OK, and then we save this. Now we can see that we have 3 of these points. And of course now this, if we update the preview, you can see them grow and then shrink again. That's actually pretty cool, I think. Well, yeah, anyway, now we have 3 points. We have one which has just a tangent out. We have one which has a tangent in and out. They just happen to be 0, right? Yeah, they are 0. And then we have one which is has a tangent in, no tangent out. That makes sense. Okay. So that's the data. This kind of data, we're gonna need to actually put that into code form. This is of course JSON, this work file. But that shouldn't be super tricky. I went ahead and prepared for this stream a little bit, just a little bit, by actually taking the, let's see, shut that down. If we look at the C++ code for this, let's shut that down again once more. Look at the C++ code for the curve node. Well, actually, we have it here because I already looked at this earlier. So this is what the interpreted version looks like. This, of course, is not interpreted. This is native code, but each node in the interpreted version has a little bit of native code that can then actually like do the thing that the node does, right? And here we have get pin value, which is in many ways the same function that we will implement there on the Zig side. So it gives us an X value, which we read here from this input pin, and then we write to the output pin. And so the meat of the thing is here in this curve2d class. Curve2d has a function called getY at x. GetY at x looks like this. It does some sanity checking here in the beginning, and then we have a loop which kind of just like finds the cubic Hermite spline and the point from that right here. So what I did was I ported this thing to Zig. I've never actually even run it. So, and if you know Zig, you know that Zig is lazily evaluated. So I don't actually even know if this compiles, but it should. Here's the same thing in Zig. You have those same sanity checks at the beginning, and then you have the same logic here, because of course we're gonna need to actually sample that curve somewhere in the native one as well. So I went ahead and added this to Zig so that we can actually read these curves, sample them. And here we have those points. So we have X and Y, we have tangent in, tangent out, they're all floats. And we have a continuity value, which is either smooth or step. So if it is step, we quite simply like sort of snap to the next value, or the previous value here in this case. I don't think I've actually ever really used that with the curves, but it was there in the C++ version, so let's have it here as well. And you just initialize one of these guys by giving it like a slice of those points. And so we should be able to just use all of this together in the node to have it do things, right? To have it do things. I think the first thing that we should do here probably is should we go back here to the effect that we were looking at, color test, and let's run this again and make sure that it looks like we expect it to. And it does. So we want to achieve this in the game, and the way I'm thinking we're going to do that is we're going to take the code this generated for us. Yeah, we don't need that. We need the first node and then everything after the first node. Let's copy all of that. Copy and put it into here. So testing color test. This is the thing. I'm gonna plonk this in because currently there should be no curve. Yeah, there's no curve nodes in this at all. And again, this is the way that I currently have to like deploy this code, right? So now that we have this, now if we search, we have this curve node. So this is the new node that we put into the thing. And we can actually run this already. Let's make that like a number 1. Just scale is 1 always. Oh, access denied. That's because this is running, and this is, even though it's not using the DLL, it's loading the DLL. Let's make sure this builds, and maybe we can have some nice simple little test level here. Let's do plane and car. That should be a super simple level. Just quick to load. And if we press P, you can see that okay. Now we are indeed. Again, it looks exactly the same as before because we're just hard-codedly outputting the number 1 there. Right? If we make it 5, we should see some change to the thing. Oh, that's not the correct one. I want to run it from this one. Alright, and press P, and now you can see, yeah, they're much bigger now. They're sort of intersecting. So the thing is running. Now we just need to input that curve business there. And the way I propose we do that is by looking at this stuff in the JSON. Again, this is the JSON stuff, like the work data. I'm gonna copy those keys and I'm gonna plonk them into this zig file here. Just comment that out like so. So we know those are the keys that we're gonna actually want to see. So let's do a little bit of magic here, which we can then, just to make sure that this actually works the way we expect it to. We can then, after we know that it's working, then we will write the code generation for it. So it works for every case. So this curve here is sampling from node number 8. So number 16 is sampling from node number 8, normalized age. So we can do, to get the x value of this, first of all, we can do const x is self kernel node number 8, node 8, thank you, get absolute age. That's the x value that we're going to want to plug into our curve. Right, and the next thing that we're going to want to do is we're going to want to have probably as just a definition up here, because this, again, this we can hard code all of these things because we're generating the code, which is pretty cool. So we can like compile time know a lot of things. So let's have a points declaration up here. We're gonna do a sprinter curve to the point. How was the syntax? I think it was like this, right? Like that. Any Zig gurus in the chat can can shout at me if I do something wrong here. So we have a point, and we do x is 0, y is 0, tangent in is 0, tangent out is 0, and continuity is smooth, something like that, right? And then we just do this, and we have a bunch of those points, and that should be good. And then we can do curve is sprinter, curve 2D, init with points. And then we do not return 5.0, but instead we return curve get y at x, like that. And that's it. This is the runtime part of the node done. It's that simple. Now we just need to generate this business here. So let's just I'm gonna just copy these things by hand. So the first one is continuity. I bet that is a smooth continuity. Let's go have a look here what it actually says in the where's that actually even coming from? I have no idea. Okay, here we can see. Smooth is 0. Good. Like I expected. Because of course it is a smooth curve. So we have 3 points. Let's get rid of the last one. We have 0, 0, 0. This is not 0. This is something. So that's tangent out. And that would be that point. Then we have the second one has an x value which is non-zero. And there's a y value which is non-zero, but the tangents are 0. And then the last one has an x value of 1, a y value of 0, and it has tangent in. Right, that should be it. That should now be what we actually need our code generation to create for us when we have this sort of data. What array literal requires address of operator? Okay, just not address of there, I bet. Yeah, look at that. So let's see. Does that actually look the same now? We're testing all kinds of things. Now I'm starting up another Visual Studio. No, thank you. No, thank you. Go away. We're testing all kinds of things here. We're testing the curve sampling code itself, actually. Okay. Yeah. I mean, it is clearly growing and shrinking, but I don't think that looks the same as it does in that other, in this preview, right? It should look like this. So what are we doing wrong here? Normalized age comes in, and then we're feeding it to number 17. So number 17 is sampling. Node 17 is right here. It is sampling its S value, which is the scale, yes, because it sets the scale here. Okay. Sampling its S value from node 16, get result, which is here. And then we get the absolute age. The absolute age. Oh, absolute age. Oh, there we go. Normalized age is what I want. Yeah. Yeah, not normal, not absolute. Well, I mean, you can do normalized age, but that's not what we had in the that's not what we had in the code or in the data there. I'm not gonna be able to build that when the game's running. Okay, let's see. Is that better? Yeah. There we go. Right, so normalized age, of course, runs from 0 to 1, during the entire lifetime of the particle. I'm just gonna get rid of the terrain here so we can see this a bit better. Yeah, it runs from 0 to 1 during the entire lifetime of the particle, while the absolute age, in this case, would have like covered just the first second, because the absolute age is in seconds. Okay, cool. So now we're not done with the node, the curve node yet. Now we just need, now we know what it needs to look like in this very particular case, and now we're gonna have to do the code generation for it. But that's pretty cool. I like this. I like this effect now with these small things sort of tapering off there towards the end. Looks fun. Cool. So, how then do we do the code generation? And that is, of course, a question. I don't think we're not gonna need that. In fact, we're gonna need it to be shut off so that we can actually modify the code here. And we do know that this is like the entirety of the node in its current form. So we're gonna put it here in commented out form. Right. So this is a declaration. This is not a field. This is a field. So it's like per instance of this thing, of this node. There is of course only ever going to be one instance of this node because it's very highly specialized for this case, but I still think we're gonna create this as a declaration, because that way it is like guaranteed to be constant data. There's really no need for it to like take up any runtime memory. Well, it will take up memory, of course, during runtime, but it goes in the correct section by necessity. So we can actually put some declarations here. Add declaration. Right? Something like this. And this actually just takes a line of declaration. So we can actually do that, and we can do the end directly. Right? Something like that. And then in between these, we're gonna have to actually loop over the data. This convert to sprinter. This is the function that that exports the data for the interpreted version, and here we have the native version. So we need to do essentially kind of like the same thing here as we do here. And what I have done here is, what have I done? We have a curve here. Right, so here we have this pre-loop and post-loop stuff. This is stuff that originally comes from like the XNA framework. So it's actually not my code. It's just like some MIT licensed mono XNA stuff that I used for these curves some years ago. Hello, explicitly. Welcome to the stream. What's happening? It's pretty slow stream today, but that's completely understandable because the time of day being what it is. Most of the Western world is like either at work or I don't know, at home sleeping. Let's see. Load from JSON. Aha. That's how I do it. Curve 2D. Can you please show that to me? Yeah. So here we have actually the points in the same sort of format that we want them to. Let's see. Where'd you learn coding? Mainly C++ looks good. And where am I from? And how am I? I'm good, thank you. How are you? And I'm from Finland. So this is southern Finland calling, which means that It's like early afternoon here, or like mid-afternoon. I typically stream a bit later in the day, so that like actually have some people tuning in. But today it felt like an afternoon stream sort of thing. And where did I learn coding? I don't know. I mean, I've worked in the games industry for like a pretty long time at this point, and before that I worked as a programmer on non-game things. And before that I actually went to school where we did quite a bit of coding, so, you know. I like to say that I'm like mostly self-taught. You just make enough stuff and then you kind of pick up on how things are done. But thank you if you think it looks good. I'm not sure I agree with all of that. And yeah, here we're actually like, yeah, C++, there's a little bit of C++ going on here. Here's, for example, C++, this curve thing that we looked at. But what we're doing currently is we're actually generating Zig from C#. So two other languages going on here. And right, I've been yapping so much. I'm gonna go get a glass of water, and then when I come back, we're gonna start tackling this curve business. 1 second. Rightio. So I'm kind of losing my voice here already. That's not good. We can see that this function here, this get result function, is mostly just the same thing all the time. Just get the x out of something, then we sample or we create the curve, and then we sample the curve and return it. This, of course, is a problem. Like, what is this? We don't know that it's going to be node 8. Nor is it necessarily going to be node 8. So what we need to do here is we need to use something called a fragment. See, do we have any fragments around here from any of the other nodes? Here's a fragment. Let's copy that piece and copy it into our curve node. So rather than hard coding self-kernel node 8 get norm age here, I'm going to put a fragment here. And we don't have a velocity pin, we do have an in pin, and that is what we want to use here. So this thing will actually then get replaced with whatever whatever value is actually plugged into the pin, whether that be a constant or a reference to another node or whatever. So this should be the get result stuff, and it references something called points with the big P. So we're gonna have to create that, and of course we kind of already started doing it here, but it's empty, so we can't have that. So let's do the same thing we do here currently. This is a little bit of a hack. Currently we don't have a conversion function making a basis curve 2D out of a Microsoft XNF framework curve, so we run it through JSON to create a conversion function instead. Yeah, I probably wrote this like 5 years ago, and I still don't have a conversion function. So LOL. We're gonna do the same thing here again. And in this curve 2D, we have points, and the points have all of those things that we actually want. Our point is actually a list, right? So if we go and have a look at 0, now we can see we have x, y, tangent in, tangent y, and continuity, and we want exactly those things. We just want to print them in this format. Right. And I'm gonna take one of these lines. I'm gonna gonna format this so that we can actually use this with the string.format statement here. Something like this. That actually needs to be like a double squiggly bracket, and that also needs to be a double squiggly bracket, because otherwise it kind of treats them as like these formatting squigglies, which we don't want. So 0, 1, 2, 3, and 4. Right. Let's see. I'm from India. Well, hello India. I only know Python and what's that? Lilt. I don't know what lilt is, but but yeah. Let's see. We'll be tuning in later. Your code looks better than mine. 12th exam tomorrow, so I gotta study. Well, good luck on your exam, and by all means you can tune in later. These things will also be available as VODs on the YouTube channel though, so I know quite a few people actually consume them that way. But yeah, go study. Your exam is more important than this stuff. Maybe we'll catch up later in an upcoming stream. So for each, let's do point in curve 2D. Not a large C, please. Visual Studio wants to very excitedly make it a capital C. And we're gonna take all of this, and then we're gonna do code gen node, add declaration. We're gonna start with some indentation here. Actually, like quite a few lines of indentation. No, actually, no, we don't, because the code generation system handles it. So we just need one level, which is 4 spaces, if I remember correctly. This, of course, needs to be a string.format, wrapped in a string.format, like so. I'm gonna make the code just a bit smaller so that I can fit it on the screen here, like this. And then we're gonna need to feed this thing its data. So that would be point.x, point.y, point.tangent in, point.tangent out, and now I'm confused about this continuity thing, because I think it might actually write it as a string, won't it? So I'm probably gonna have to do something like this. If continuity is smooth, then we do 0. Otherwise, we do 1. We just have those two modes. Have you released any C++ courses or streams teaching it? No, I'm not a teacher. I'm very much just a developer. Hope stream gets more reach. Yeah, it will eventually. Like I said, this is just I'm a little bit too early today with this stuff. I bet it will eventually get more reach. I'm not very worried about that. I mean, I'm just working on my game here, right? Trying to release Traction Point next year, and for that to succeed, I'm gonna just have to keep working on the thing. So this is just one way for me to work on the thing, and whether or not people tune in, that's not necessarily the main thing. And even though it is of course nice, it's nice if people do that. Okay, we're gonna have to probably add some decimal places here. How do we do that? It's something like 0, something like that. Is it? Or is it maybe something like this? Yeah, that looks better. So this would be 3 decimal places. Yeah, we don't want any F letters behind it. That's not good. So we essentially only want like that piece. Let's add like 5 decimal places. That should be good for these curves, I think. So we want that for the first 4. Oh, not that way. We want a colon there in between. colon there in between. Do you enjoy streaming programming? Yeah, it's not bad. I can do every kind of programming on stream. This kind of thing is pretty nice because I've been doing this now for a couple of days. Doing this sort of code generation thingy. So I kind of know roughly what is coming down the pipe, right? And so I can do this kind of streaming and programming kind of okay. If I'm working on a completely new system, I can't really do that on stream because I'm just gonna be sitting like staring at the screen for a long time, going like, and that's not very interesting for you guys to watch. I think we're done. I think we're done with this. I'm gonna leave that thing there in the comments for the time being. But let's see what this actually gives us. So if we go into our little color test thingy here and we look for curve. So here we go. This is what it has generated for us. Some curve points. If we go and modify this, we should see the change there in real time. Actually, we should see it when I click OK. Yep, you can see the Y value there changing. And if I move this guy and then add some more points here, we can see some more points emerging. Isn't that cool? I'm just making sure here that we actually, I think we're following the zig formatting and everything. There's a colon there after, or a comma after the last one, which is how this would be formatted vertically like this. There's no comma after the last parameter here, or whatever this is called, initializer list. So this would not be vertical, this would be horizontal like this. This looks cool. Okay, so let's undo all of that, get back to our stuff, and let's just make some small little change to this thing. I'm gonna make this 0.5. Yeah, 0.5 is good. And let's make it sort of like, just before it goes away, it kind of like jumps back up a little bit. We should be able to see that in the output, right? So I'm gonna take all of that, I'm gonna copy it and plonk it into here in the color test. This is exciting because if this now works, that means that we are going to be able to do one of the actual particle effects in game. Okay, we have an error somewhere. Where's the error? Unsurprisingly, it's here. Oh, printer. Yeah, I'm missing an S. I'm missing a letter S. Because this is not supposed to be printer, it's supposed to be sprinter is the namespace here. So there we go. Let's build that. Okay, it doesn't build. What's that? Ah. Yeah. Yeah, that can't actually be that. I'm gonna have to make one more little thing here. So this would be, if it is smooth, it would be dot smooth, right? Dot smooth, because if we go here and have a look, it is smooth and step. So dot smooth and dot step is what this actually needs to be. This this continuity thingy. Let's try that again. Curve, and there we go. That looks better. I'm just gonna copy that piece of the pie. Search for curve here. Oh, not there, but here. Here we go. So just plonk that in there. Okay, I didn't manage to copy it, did I? I need to right click and select copy. That's annoying. Boom, there we go. So now, with a little bit of luck, should be able to, yeah, now it builds. Okay, cool. So, what do you think? We're gonna see the little thing at the end there. Hoping we will. So they should. Oh, you know what? I know what happened. I know what happened. I didn't actually save my little change that I made. That's fine though. So let's redo the change. This will be almost disappears and then it goes back up. Now I'm just gonna copy that again and let's do copy and plonk that in there. Rebuild. Fortunately, the builds here are pretty quick, even though we're essentially recompiling everything. Well, that's not true. We do have the SIG cache there underneath. Okay. Now we can have a look. Let's see. Yep. Now we can see before they go away, they start growing again, and then they die. Just before they die, they grow a little bit. That's kind of fun. Fun effect, I guess. And yeah, this is the terrain again. This weird thing there in the sky. The terrain from underneath. We can just get rid of the terrain. Bye bye. Nice. Almost looks like bubbles popping or something when it goes back up. Interesting. Okay, cool. That would be that. That means that with a little bit of luck, we can actually export this dust particle now. So material effects, cartoon smoke, continuous. Yep, we don't get any errors or warnings. That's great. And how big is this thing? With all of the things in it. 1511. And we should have some curve data here. Kind of importantly, and we do. Look at that. And that, of course, is this curve here. Cool. Cool. Yeah. Excellent. I do wonder if we should actually name that something else. If that is too generic. We're gonna have some naming conflicts at some point. I don't know. I think it's probably fine. Let's keep it as it is for now. So let's copy this thing. Copy all of this. From the first node to the very end. Yoink and copy. And then put this into this thing. I had already added the resource path and the hash there, which the editor currently doesn't figure out for us. So now if we undo these changes that we made in the very beginning of the stream to make this actually compile, what do you think are the odds I'm going to be able to compile this? Yeah, it gets a little shorter. It gets about 100 lines shorter when we save this, because the SIG formatting takes over and formats this thing according to how SIG wants it. Seems like my code generation doesn't quite adhere to the SIG formatting rules. That's probably not a problem, but maybe that can be looked at as well. Anyway, it does build. That's interesting and a little scary. So this is a considerably more complex effect. This is like parameters and things driven by the game. Let's see what this actually looks like in the game now then. So let's go to an actual level. Refinery blockout. And okay, we have some even dust. Okay, you can see it sort of disappearing. Well, if it was working 100% correctly, I would be kind of very suspicious that are we actually even running the native one. Okay, I think I kind of know what's going on here at a very high level. So when a wheel is no longer touching the ground, we essentially relinquish control over that effect, and when we tell it that, like, something like released when finished or whatever, we tell the particle system engine that, like, this effect can play to the end. It can no longer spawn any new particles, but it can play to the end, and when it has done that, it can be released. And I'm thinking there's something wrong with that now, because it just immediately goes away. Like, if we get some air time, as long as we stay on the ground, you can see like this, it works perfectly fine, which is fun to see. But if we get some air time like that, you can see that it immediately goes away when the wheel is lifted off the ground. So that tells me that there's a problem with the release when finished logic there for the native ones. So we're gonna have to see what that's about. But hey, other than that, it looks correct. It doesn't look super good, of course. It's kind of a placeholder effect that just has kind of just been there. But it looks correct, and it also does the color correctly. If you drive on the road, it becomes brown. If you drive off the road, it becomes gray. That works as well. Okay, that's cool. Let's have a look here. This is the game. So it's called something like tire effects controller. Ah, yeah. I actually happened to just hit it immediately. It's not a very large file, this, but release when finished and 0. So we zero out the pointer because we know it's no longer safe to actually do anything with it. And we call release when finished. Release when finished probably can be found in the C++ side, which is here. Effect instance, release when finished. So we do have a little bit of logic here for the native side stuff, but not a whole lot. But yeah, I think this waiting to be released is the important one here, right? Yeah. Let's search for that. See if we can figure out this bug which is plaguing the game. I'm gonna shut that down so we get rid of the background noises there. Waiting to be released. It's initialized to false, is set to true. Ah, yeah. Yeah, I think here's the bug. Here's the bug. So particle store is only currently used with the interpreted versions. So this particle store is going to be empty. If we are running natively. And so here in update, if this is true, in the interpreted ones it waits for this particle store to not have any active particles, and when it doesn't have any active particles we release it. But with the native one it immediately releases it. Yeah, that makes sense. Okay. Now the issue here is that the particle store now lives on the zig side. Right? So we don't have a handy function for that here yet, but we can make one. Let's make one. So let's put in here is native. And I'm gonna put a to do there. That's where we're gonna call it. I'm gonna handle the native side here, yeah. Yeah. That looks good. Okay, so let's go to the DLL with all of the particle systems. Here we have the API that the game engine can call on these guys. You can see that they are exported functions, which means that C and C++ can call them. We're gonna need to add like a what was it called? Has active particles. So let's add an export function, has active particles, and yeah, we need to pass the same parameters here as we do with the other functions. Basically, like this thing, you can see that it's present in most of them. When you query something or you send something to an effect, you need the effect type, which is a U32. That's like the string hash of the resource path, and then you need the actual node graph ID. This is essentially a pointer. It's a U64, but we actually use the pointer as the value there. So that way we can actually get a hold of the actual effect. Yeah, stop all cursors. We need to do basically the same thing here. So has active particles. Let's name that has active particles, and that would be bool. And then we can do one of these guys. Has active particles. That would be a boolean. And we're gonna need to return something, so return false for the time being. And then we can call that and return, right? Return and semicolon. What's the problem? Duplicate name. Alright, it's supposed to be internal, yeah. That's supposed to be internal. There we go. Yeah, it complains about the variable. That's fine. We're gonna fix it in a second. So yeah, this is the sort of stuff that I'm gonna have to generate as well. This is essentially just like the lists of all the registered particle systems that we have. Okay, and here, of course, we are going to do return node graph store has active particles, effect type, and node graph ID. Quite simply, like so. And then here we're gonna have to do a little bit of fun engineering. Let's see, these kernels, as they're called, they should have the particle store is right here. So particle store on the Zig side is here. Oh, you know what? You know what? We don't have to do this in Zig at all. I'm realizing now. Yeah, we can just undo all of this stuff. We don't have to do this at all. It's completely fine. Don't worry about it. Because, yeah, we don't have the particle store thing there. But the particle store is really just a small class, or struct rather, which manages the SOA particle buckets. Particle store is right here. So you can see it has a merely native SOA particle bucket, or it has a list of them, 32 to be exact. It has a pointer to those. So here's a particle bucket. This is the new way that these particles are actually stored in memory in an SOA format. So you have a bucket of particles. I think they're 256 per bucket, yes. And Zig merely has a pointer to these guys. And so the actual creation of this happens on the C++ side. I completely forgot that. So we can, and we will, actually just use that, won't we? Let's have a look, see here. Here we go, yes, buckets. Static vector of SOA particle bucket. Excellent. So let's see, has active particles. Where do we actually call this? It's called in many places. Particle storage, particle system. Oh, that's the old particle. That doesn't, yeah, that's not interesting at all actually. Particles, particles, particles. None of that is interesting. It's only this place. Particle store has active particles, and yeah, excellent. This is really good actually, because we can basically just do the same thing here as we do here. So how do we do this now? Let's add a function to this type. I was considering how to do this, but yeah, I think this is going to be good. So let's add a boolean here. Has active particles. It can be a const method. Why not? And if we are native, is native, then we're going to do the to do thing. Else we can return particle store has active particles. This thing will eventually go away, but it's still there because I haven't ported the interpreted side to use these SOA particles yet, but it will be eventually the only thing that we have essentially. So we can probably do like basically exactly the same thing we do here. Back to my to-do, there we go. To-do. And so this would be buckets is right here. We have SOA particle bucket. I think that's a pointer. And there we go. That should be it. And then rather than calling directly on the... That's not what I want to do. Rather than calling directly on the particle store here, we just call our new member function. We can take those away. Like that. And then this thing handles the separation there between one or the other. That should be good. Let's see if that works. Alrighty then, let's have a look-see. So now if we get some airtime, you can see the things continue until they actually eventually die. We should probably print something when one of those things die, just to make sure it actually happens, right? So, because there should be just like a whole lot of it happening all the time, and we can print here like if is native. Just copy that guy. So native particle effect being released, something like that. And we should get just a whole lot of those outputs just driving around the place. There we go. Now you can see that it's actually just like happening all the time, even with just the one vehicle here. That's cool. Okay, this is going actually really well. So we have two other particle effects here that are kind of, I don't know, like plaguing the performance or not, but like they should definitely be ported into native form. One is this other little thing here that we have going, which you can see better if we are driving very, very slowly. Is this little, I don't even know what to call that. We can have a look at what the name is actually. But you can see this little sort of almost looks like pebbles that are sort of coming off the wheels. That's also a Merlin particle effect. It is actually a billboard rendered particle effect, as opposed to this dust thing, which actually uses meshes, like those balls, spheres, are actually just meshes, sphere meshes. But yeah, these little pebbles or whatever that come off the wheels, they are actually billboards. And I don't think we have support for native billboard particle effects, so we should make that happen as well. And then finally we have the massive one, this smoke pillar thingy. This is kind of like the largest and most complicated effect currently in the game. This is all just one effect, so everything with these like embers or whatever these are flying off the thing, this is all just one big effect, which we should definitely make native as well. But I'm thinking we're gonna start with that with those pebbles, make sure they work. Because this is just going so well. I was kind of worried of running into some issues here, but kind of doesn't look like it's happening. Kind of just looks like things are working. So let's keep going for a bit longer, shall we? Yeah. Let's do that. I'm gonna take a quick pee break and then we'll continue. So I'll be back in like 5 minutes or so. Righty then, we are back. Right, let's actually have a look here at what that little particle effect is actually called for playing. That's not the correct VS Code. This is the correct VS Code. Try to remember here where I actually have those paths. If we can find the release. Yeah, here we go. Long slip effect. Lat slip effect. Right, I think it's actually the slip effects are those effects that we have, and then the dust effect. That would be the one that we already did, right? Let's see, tire dust particle effect. No, that's not the one. That's not the one. Where do we load that guy? We don't load it here at all, ever. It's loaded somewhere else, is it? Okay. Yeah, that's the instance, and what we actually want is this one, tire dust particle effect. And here we go. Okay, that's better. So yes, the cartoon smoke continuous, which we already ported over to native. That's the tire dust particle effect, and then we have tire long slip gravel and lat slip gravel. I bet those are the small ones. I don't know why we have like different ones. It's possible that I just made one and then sort of renamed it so that I could have two different ones. But let's have a look. Let's see what that actually looks like in the editor. Yeah, so they're actually just here. The other two ones. Okay, I can already see we have some what do you call it? Some nodes that we don't have native code support for. So there's going to be some work here. Native code window is there, and we can see, okay, yeah, we don't have billboard renderer, particle renderer support yet. That should not be a particularly tricky thing to add, but we don't have that. I don't think we have the for loop either. Let's play this thing and see what it actually looks like here in the editor. So yeah, here you can see. It's just almost like, it looks like it's kind of like pouring sand or something. And that's fine. We have the strength parameter, and that's the only parameter we have. So what do we have here? On start should be fine. Repeat node is ported over. For loop, I don't think we have. I'm gonna just create like a good old-fashioned physical list here, or list on paper. So for loop, and we already know we need the renderer, the billboard renderer. Random float should be fine. Float parameter is fine. Emit particle is fine. Set particle velocity is fine. Direction 3D with deviation is fine. I know this because I've done like all of these things today. Float operation, random float, I think those are both fine. Store particle value is fine. This one is not. Comp-wise random vector, I don't even remember I had that. So let's have comp-wise rand vector. That one we need to port. Set particle color is fine. Vector operation we don't actually have, believe it or not. Vector op. We need to port that one. Color vector is fine. Swizzle vector is also not created. Okay, that's gonna be interesting. Update particle is fine. Apply particle force is fine. Particle data is fine. And curve is fine as of about an hour ago. That's fine, that's fine. Decompose is fine. Float operation is fine. Scale rotation. The rest of them should be fine. Yeah. Okay. So the rest of this should be fine. We do have 5 nodes that I need to port though, if my notes are correct. And I think if we just look at the other one, this was the longitudinal, so if you look at the lateral slip, it's exactly the same thing. I just made it into a separate file here so that I could potentially have 2 different ones. Okay. Well, let's quite simply go ahead and start porting these one after another. We can't generate native code because this thing says no code gen method defined for the type billboard particle renderer node. So it errors out if you don't have any code generation functionality. All of the nodes need to support code generation for code generation to succeed, unsurprisingly. So let's go and start on the billboard particle node. It's right here, and we can probably actually, I'm just gonna close all tabs but this and do mesh particle renderer node, and I bet we can probably copy paste this stuff almost verbatim, not quite, but almost. So the mesh particle renderer node has a few more fields. We have a material resource path, sort particles, true false. Here we have mesh resource, material, sort particles, and light probe support. That's all fine. We don't have that many for the billboards, but let's bring this over anyway. And we need to specify that this is specifically for the billboard particle renderer node. So that guy goes away and that guy goes away. Alright. And then we have basis string interrupt mesh resource path. We don't need that one. We don't need that one. And if we go and have a look at the already converted, so here's the mesh, here's an instance of the mesh one. We should be able to find here fp effect instance get bb renderer, billboard renderer. So that's what we want to use here instead, bb renderer, and it only takes the material and whether or not we want to sort the particles. So we can take the mesh away, we can take the light probe support away. And then there should be also an equivalent for this guy, so register mesh renderer. Let's have a look here. Register bb renderer, and the thing is exactly the same. So then I bet there's also a release bb renderer. Right. Let's see. BFH Corny BFH asks, is there a specific reason for using C# for the editor, or is it just a preference? I don't know if it is even a preference. It's just basically what I happen to know, right? You kind of just need to use whatever you know, unless you specifically want to learn new things, of course. But no, there's not really, no. It's kind of just what I happen to be somewhat comfortable with. And of course, C# is pretty good because it has a huge ecosystem of like libraries and everything. So in that sense, I'm not a very good C# programmer, I might add. I'm doing pretty old school C#. Okay, let's have a look here. What do we actually have? We have a renderer out pin, which is, yes, it's that one. We register a symbol on output data pin renderer. So the way this works is that if we have the mesh particle renderer here, in the init for this node, which is run when this node is created, we get the renderer from the C++ side. we store it in the renderer pointer. You can see printer C++ pointer here. Then we register the mesh renderer, and we get a renderer ID back, which we store here in this renderer ID field. And then when we deinitialize it, we just unregister it, or release it rather, and then set this thing to 0. And then we have this call here called register symbol on output data pin, renderer ID. So this of course is the same as this field here, which just means that if another node wants to get the renderer out of this node, they know that, okay, they can use this renderer ID as the field name. So this should work exactly the same here in the billboard renderer. Should be no difference at all. So that's nice. I think we are basically done, aren't we? Probably. I was just wondering, due to all the editors I work with were all developed in C++, so I thought maybe I was missing out. Yeah, I mean, I wouldn't say you're missing out. I probably wouldn't necessarily write an editor in C++. I don't think C++ is a terribly good language for that, but of course it depends on what kind of like framework you have around that. If you're working with Unreal, for example, then it probably makes sense to write your sort of Unreal adjacent tools in C++ as well, because then you can use Unreal's UI functionality, blah blah, all of that stuff. And I don't know how things like Godot do it, for example. But if I was to just like start from scratch and go like, how should I write my editor? I don't think C++ is necessarily what I would go with. Although it might be a pretty good choice if you're using something like Qt or whatever and want to support multiple platforms. Like I'm using WinForms. This is all Windows Forms. Even this editor here, this node graph editor here is Windows Forms, which of course means that I'm kind of stuck on Windows for the time being. It's kind of annoying in a sense. Hey, Xluxy, welcome back. What's happening? But yeah, I wouldn't say you're missing out. C++ is fine. C# is fine. Lua is fine. JavaScript is fine. Zig is fine. Just plain C is fine. Use whatever you want. They're all fine. They all have their wrinkles and they all have their beautifulnesses. Okay, I'm gonna put in like a stub for all of the things that we are missing now. So we already implemented this billboard thing. That's why it's no longer complaining about that. But we have 4 more that it doesn't have a code gen method defined for. So this component-wise random vector node, this guy, is the next one in line. I'm gonna add stubs for all of those. And that means that we can generate the code again, which means that we can, for example, see what this billboard renderer node actually generates. So let's go to the for loop node. Yep, this doesn't have anything at all, like I was expecting. Yeah, I can just copy one of these guys from. Just add a very basic, take away basically everything. Comment that out, and then add those usings there. For loop node. That's basically like the minimum you need to have for the code generation to actually go through. Component-wise, random vector node is right there. Let's add one for that as well. Come on, show me the thing. Thank you. Then we have vector op. And then we have the swizzle as the last one. So essentially, my goal with the current particle system work is to have all of the particle systems that are currently in use in the game be native particle systems. And then at some point I have to make the actual compilation of these guys be really, really smooth and nice and happen in the background, so that you don't really have to care about that stuff all that much. That's not gonna happen yet. But yeah, we have basically just like this tire long and lat slip gravel effect, and then the smoke stack, smoke pillar. I think those are the main ones that I would still like to have working as native ones. And so that means just like porting a whole bunch of nodes over, essentially. That's what we have left. Okay, so now we have another error here. Output data pin result of node 13 doesn't have any symbol registered. So let's go have a look. What's node number 13? Right, this one. Okay, compwise random v, random vector. Yeah, if you turn on the ID, some of those texts don't really fit. But yes, this one. And now basically this thing is complaining that, hey, I'm reading this value from node 13, but node 13 doesn't give me anything on this output pin. Output pin result, that's this thing. This compwise random vector node doesn't actually have any value plugged into this result pin. That's what this is about. So let's make that happen. I'm gonna just stub that out. Where should I copy that from? Probably like random 3D vector node. I bet has, yeah, get result vec variant. Excellent. Let's get that one. What's it called actually? It's called result. Good. So then we can use this directly. And I'm gonna copy. I'm gonna remove all of the things from the actual function, and then just do 0, 0, and 0. That's actually not the one. It's called just init3 if we give the components directly. So now we create a function called getResult, which returns a sprinter vec variant, and we return just a 0 vector. Oh, and I managed to copy one too many squiggly brackets. And then we need to tell the system when someone is requesting a value on the output pin, which is called result. So I'm going to plug that in here, result. We call this result pin. When someone is requesting a value on that pin, we need to register a symbol for it. So we give it the result pin, and we tell it to call get result, and it's specifically a function, so we give the empty parentheses after the name there. Right, this is now the sort of minimum that you need to have for the code generation to generate anything sensible for that node. It's not correct, of course, but now we can proceed. And now we have the same thing here for another node, which is probably like a swizzle or a vector op node. Let's see, number 26. Number 26 is a vector operation node. We can do the exact same thing for that, and it should solve it for us. So I'm gonna copy those vector op node. Again, it's called result. So let's call this as well. Result pin result. There we go. And this should also return a vec variant. And I think the swizzle one is probably going to be something similar, so let's do that here as well. It's also called result, and it's of type vec variant, so I can do the exact same thing. exact same thing here. Good. Okay, now I think, if I'm not mistaken, I think we should be able to generate the code for this. Hey, look at that. Yeah, it looks like a very small little effect, but it's actually like potentially even a longer piece of code than the dust effect. We have quite a few nodes here. So I'm just gonna strike out my billboard renderer node because that one we actually did properly implement here. So there's some interesting nodes coming up. There's a for loop node, which is this one, which is essentially the same as a for loop in a programming language. You enter from here, you give it a first index and a last index, and then it fires this thing every iteration. You can read the index out of this guy. And then you complete it, and it fires this. So that's an interesting thing. It has some state and stuff. Component-wise, random vector. I'm gonna have to look at what this does, but I bet this is like a minimum and maximum for x, a minimum and maximum for y, and so on. Then we have vector operation. This is like multiply, add, sub, divide, cross for the vectors. That should be interesting. And then swizzle is right here. Yeah, so xxx1. How does that actually work at runtime? Let's see. Swizzle. Right, so it gets the element value. This is the sort of meat of the node. We get the input value, which is a vec variant. We get an output, or we create an output value, which is also a vec variant. And then we get the element value, state exp. That's an expression element, which we can have 8 of apparently. X, Y, Z, W, 1 and 0. Right, so you can have XXX1, or you can have Y, Z, W, 0, or you can have 1, 1, X, Y, any combination of those. How do we figure out what that is though? Exp. There might be a little bit of logic here on the C# side actually for that. Swizzle. Oh, we are already in the swizzle. Yeah. So this is a case where I think we can actually make this just so much easier in the code generated version, because we can just hard code the expression out here. So parse expression. Luckily we can use all of this code for the node, for the native nodes as well, right? So convert to Sprinter, and here we have the stub for the native code generation, but we can just call this parse expression here in this one as well, and this gives us these same elements. So that's neat. Here we actually, we push them to stream because it needs to be then put together at runtime in the interpreted version. But we don't need to do that here. We can just immediately swizzle it in place and do all the work up front. So that's really interesting. I think. Cool. Yeah, here we can see like this is another important part here. Get element value. So 1 and 0 are just constants. and then we basically switch based on whichever element we want, and then just read it out of the value like this. But yeah, we can do all of this at compile time or code generation time, which comes even before compile time. Excellent. Okay, that's fun. Let's start with the for loop though, because that's the next, or the first, shall we say, node there in the node graph that's going to be actually executed almost immediately. From some 0 to 10, so this actually runs like 11 times apparently, because it's like inclusive when it's first and last index. Let's have a look at what that actually looks like in C++. So for loop node, and here is the meat of that node. So if we are entering through the entry pin, we don't have any other than entry pins, do we though? We have first index and last index. They're not execution pins, they're data pins. But yeah, we still check that we are entering. If we are entering, that should be the only one. We should basically assert that we are entering from the entry pin. And then we have the first and last indices. And then this also supports a backward loop. That's cool. First and last are the same. And then we just start new cursors on the output pins. Yeah. And then we exit via the completed one. Yeah. So pretty simple. This should be quite simple to do actually. Gonna drink a little bit of water before I keep yapping. Alrighty then. So I'm gonna drag this off to the side so that I can have it as a reference. Because like the code that we're gonna want to generate for these guys, these native nodes, it's basically like mirrors of the C++ nodes that the interpreter then runs, which should make sense, I guess. So. Cool. First of all, we have some pins that we want to declare. We have a pin called in, and if a pin is in parentheses, that means that we don't actually write that name there in the UI, which can sometimes be handy to kind of keep the UI kind of clear. So it's just called in. Then we have first index, last index. Those are the input pins, and then we have some output pins. So this is first index, last index, those are input pins. So this we need to be careful here. Input pin. Rightio. And then what's that actually? That is a that's a node pin. So we actually already have these private variables for some of these pins. We're essentially doing the same thing here. The problem is that this is a static function, this generate native code. Just get the node in here. So we need to that's why we need to get them out of the node to be able to actually use them. But it's a little annoying. Arguably. Can't be helped. You could of course just make these public properties or something. We could use them directly, but not currently. Loop body, index, and completed. So var loop body pin get output pin or throw. Loop body index and completed. Like so. And if we look quickly at the C# one again, you can see that we have a state. It's currently just a current index integer, which means that, like, I do wonder if we actually need to store that, because this thing is sort of like blockingly just, you know, running through all of these things. There's a for loop and a for loop, essentially. But yeah, maybe we'll do it the same way. So if we want to replicate that in Zig, what we need to do, of course, is CodeGen node add field. And we can call it the same. We can call it current index, and it is it's an integer. So let's make it an integer here as well. 0, like that. Oh, we need the semicolon. And yeah, you need to put a comma there because these are just treated as strings. It just pastes this into the position in the struct where we want the fields. Right, and then we want an update method, or update function. With an update function, and I'm going to copy that from something that I know has update functions. The repeat node, for example, is a good example of that. Because the indentation here is a little fiddly. This is something that I'd like to actually improve later on, but yeah, it's a little fiddly currently. So the update function is you don't give it the. You basically only give it the body of the function. So you can see it just starts with an if here, and then return continue. Well, I think return continue is what we'll do. So that's the only thing that we're gonna keep and delete everything else. Maybe not actually. Whatever. Let's delete everything else for now. And actually, let's do like something like this. Maybe this is a slightly more appropriate update function for our cases here. Take some of this stuff here. So basically, we want to assert that we are entering through this input pin or in pin here. So that's fine. We want that. And then we want to get the first and last indices. So let's do const first index. First index. And we want to read that from this first index pin. And we can do that with a fragment. Let's go to fragment input pin value and just give it the first index pin. It's there. And we'll copy that to the same line or same indentation and call that last index and change that to last index as well. So there we have the first and last indices. And those things also actually have inline values. So an inline value basically means that you can either plug that value in through the pin, or you can hook it up. You can use one of these values that are like directly input into the node like this. So if you have an int just comes from another node and we plug it into there, you can see that the field actually kind of goes away. You can't have both a pin and an inline value but the pin can be associated with an inline value. And so we need to support this. And we do that by telling the code generator that hey, if the pin isn't actually connected with anything, we register the inline data for the input data pin. Input data pin being first index pin, and the value being node.firstIndex to string. The same thing for the last value. Last index pin last. So it wants a string here as the second, because again we're generating code, so it just wants to like paste something in there. That's why we have to use the toString there, because these are integers. So now we get sensible stuff here in these two variables, even if those pins aren't connected to anything, which is exactly what we want. Okay, and then we have basically, we have these things. We have the forward loop, the backward loop, and then the case where the first and last index are the same, which just means that we essentially don't have a loop. We just run it once. And then we exit via the completed pin and return continue. That's fine. Let's actually copy all of this stuff into the code in here. That's called first and last. We can just make it the same here in Zig as well. So forward loop. Now this for loop, of course, won't really work. Doesn't look like that. And backward loop doesn't either. And the way we exit here in this is that we immediately transition to the target node, which we can do with this fragment. Exit via output pin, and it figures out where to actually place us. We're just gonna have to give it the correct pin there. Completed. And then we return continue. That's fine. This is going to be self.currentIndex. So that, of course, is this thing that we've declared up here, which is an i32. Gonna have to make sure that these things are actually i32s all the way. Start new cursor output on loop body. That can be done also with a fragment. Start cursor on output pin, and it's the loop body pin, like so. That would be that. So now this case is essentially handled. This is not really how we do these curly braces in Zig, though. It looks more like this. Cool. And then I wonder how to do those for loops actually here. So this should always be the same. It's self.currentIndex equals first. And we want this fragment for all of these places. And here I think we want like a three level indentation. So let's put a 3 there. Actually, this is probably 3. Yeah, this is the standard one, which is 2. This is 3, and these would actually be 4. I think that's how it's supposed to be. So now we just need to somehow figure out these for loops here. How do we do that? So maybe the easiest thing is to have var I is of i32. And we initialize it to first, and then we do a while I is less or equal to last. We do this, and then we do I plus equals 1. Might be some other way to do this nicer with a for loop in Sig, but I think I'm gonna go with this for now. So we start with I, which is initialized to first, and then we keep going while I is smaller than or equal to last. Yeah, that looks good. Let's go with that, and then we do the same thing here. We do this. So I is once again first, and I want it to go until as long as it is larger than or equal to last. And then we want to subtract 1 instead, like so. If all of this just looks super confusing, it used to look super confusing to me as well, basically 2 or 3 days ago. And I'm just like, I've looked at this for a few days now, and I'm just like, I'm kind of like seeing through this weird syntax here and going like, yeah, I can sort of see how this is going to how it is going to look. Let's see. Xluxy has a question. In your loop, it should be I, not first. Really? Let's double check that. In your loop, do you mean the first loop? So for int I equals first, that would be that part. Then we have I is smaller than or equal to last. That's that part. And then at the end we increment it. Oh, all right. Yeah, you're quite correct. This part, that part should be I. Yeah, absolutely. Yeah, that was just a copy-paste error, because like here at the end it is actually first. Yeah, thank you. That. I'm sure I would have missed that. And then been very confused for a while. But yeah, it was just because I copy-pasted this guy. Or rather this to these guys. Oh yeah, it should be I, obviously. And there's another thing that we can't forget here. And that is this index pin, which is not connected here to anything. So we could just generate this code now, no problem. It would work. But if someone connected it at some point, we would get a code generation error. So let's fix that as well while we're at it. I'm gonna copy that one, right? Something like I can actually copy both of those. So index pin, right? Let's call it get index. No, we don't need to do that. We don't need to do actually any of this, because we have it already in a field. So we can just do this, just index pin, and do current index. Probably gonna have to actually try that works, but that should be fine. And I typically have those symbols registered up there. Yeah, I can just read it directly from this guy. Courtesy of Sig's always public fields. Okay, let's go. Let's see what that gives us. So that's the node with ID 35. You can see based on the IDs how this thing was actually developed, because it's a running number. So the first node that I added was this, then that one, then that one, then that one, and then that one, and so on. So you can see this for loop was added quite a bit later, because it has ID 35. We can find it here in the code, and here we go. So now if we add like a format print, for example, which, you know, prints that value, and we can hook that up. If we go and have a look at 41, is right here. It reads the value directly out of self-kernel node 35, so this one dot current index. That's nice. And the index works as well. The node 35 is... oh, I had it there, didn't I? I had it there. Here we go. Right, so first is 0, last is 10. So now if we make that something else, we can see the thing is just updating there in real time in the code. That's neat. And those fragments also, you know, if I add this back, because if I plug this into the loop body, now it jumps not only to node 2 but also to node 42, node 42, node 42. If I copy that one more time and plug that in, now it's jumping to node 43 as well in all of these places. That's where those fragments come in. They're sort of... the code generation figures out where's this pin actually pointing, and then pastes in the code. That doesn't look good though. This doesn't look good. Why is it invalid node ID and invalid pin index? That's not good. Oh, it is. It is absolutely. It is absolutely fine. That is because this thing is not connected to anything, right? So if we add a format print here just to have something to plug it into, if we plug it into here, now we can see it. Now it's pointing to 44. Yeah. That's completely fine. I was thinking about loop body, but loop body actually starts a new cursor, or a new cursor is started on loop body. Yeah. Never mind me. I'm just bad at my job. Rightio, I think for loop is good enough for now. So let's move on to the next node here, which would be the weird component-wise random vector thingy. This guy here. So you can have vector 1, 2, 3, or 4, and I bet it gets rid of those other fields if you just have resizes the node. All of that is of course handled in C#. We don't need to do anything with that here. But let's have a look at what the C++ is doing with that node. So component-wise random vector. And here's the get pin value, and it's kind of a mess, as you can see. It's kind of a little bit of a mess. Yeah, this is an annoying node, specifically for one reason. I mentioned previously that you can associate pins with properties. So if we disconnect this guy, you get a field here, and you get a property, lifetime property. And then if you reconnect the pin, it goes away. Well, this is annoying because here you have essentially two fields, two properties. You have min x and you have max x, min y and max y, and they're both associated with this thing. Now that system doesn't give you all the automatic handling of those values as just having a pin be associated with a single value. Instead, we have to do a little bit more sort of manual work here to make this work. So here you can see in the C++ version we're trying to get something out of the data pin value x, which would be this pin here. And if that doesn't succeed, then we do like something completely different, like run a piece of code here, get random float min x max x. Now this max x here, of course, is like in no way actually associated with this pin value, but this is what we need to do here in this case, because the system can't like be associated with like multiple values. So luckily we can make this a little nicer with the node generation, because we can do all of this business again at code generation time. So the runtime will then just see a value and go like, value x is, you know, either the thing that comes out of this pin, or it will be like a hard-coded call to get random float, blah blah blah. We don't need to like try one and then fall back to the other. That sort of thing. So it would be a little nicer, but of course we still have to write that code here on the C# side when we do the generation. Anyway, I'm gonna stop yapping now and just get started with this thing. We have 3 more nodes to do, and then we can hopefully run all the vehicle-related particle systems as native particle systems, which is fun. And then we just have the monster one, the smoke pillar, left, which I bet has a few more nodes for us to implement. But that's probably not going to be this stream. Okay, let's get going. So let's find the thing here in the, I'm going to shut that down. Component-wise random vector is here. We need a result, and it is a vec variant, which we already established. And then we have some pins, so let's again declare those. Start by declaring those and just copying them down here, commenting them out. So result pin, yes, that's an output pin, that's good. Then we have X pin. That would be node get input pin or throw. That's just X. X, Y, Z, and W. X, Y, Z, and W. And that's it. Those are all the pins that we have. We have some state on the C++ side. We will actually have some state here in this one as well, because we have this random engine in the C++ side. I have sort of a standard for doing randoms here in the native code generated version as well. Let's go to random 3D vector node, for example, which has one of these things. So basically we need to add a field for the random engine, which is of type std random default PRNG, so pseudo random number generator. And then we need to initialize it. So let's add a init function line. And yeah, this looks funky because, again, because of these verbatim strings, this like needs to be indented in a funky way. Can't be helped. And here I'm using the Merlin effect pointer as the seed value. Just this the handy way to get pseudo random numbers. Just using the pointer of the actual effect on C++ side as a seed for the random RNG, basically. Rightio. And then I think that is basically it. The rest of the stuff, like on the C++ side, we have some more. We have these min and max values, and then we have the vector node type. But we know all of these. We know all of these at code generation time, so we don't need to store them here. We can just use them when we generate the code instead. So what comes to mind here is know, something like a vector node, for example. Which has something like this. Looks a little nasty, perhaps. But this adds a different get result function based on what kind of vector you actually want. So a 1D, 2D, 3D, or 4D vector. And I mean, I guess it kind of mirrors this C++ version where we have this switch here, vector 1D, 2D, 3D, 4D. So I'm wondering if we should actually just do the same. We should do the same thing here, where we just quite simply copy paste this entire switch case and plonk it into this one. So I'll get rid of that, copy that here instead. And I guess that looks all right. Now, what we have here is in some ways already what we need. We have the same thing with like X pin, Y pin, C pin, and W pin. But we have this extra complication that we need to match them against those two fields if the pin is not connected. So I'm thinking, like, how do we do that? How should we do that? So this pin, node, which I converted earlier today, does something kind of similar. It also has two fields that map to one single pin. So thus it asks the node's owner, this is the node graph, asks the node graph, hey, which pins are connected to this pin? So basically it asks, is this pin connected to anything? And if it is not, if the length is 0, then we do the random float thing. So this is almost exactly what we need. We just have some slightly different fields. Yeah, this looks actually all right. It's just going to be a whole lot of probably repetition here, unfortunately. It looks something like this. We have an X fragment, so FGMT stands for fragment. X fragment is going to be if the X pin is not connected to anything, then we want a random float of node X min, or min X rather, to max X. If it is connected to something, then we want the thing that it is connected to, just get input pin value, right? And then we can use this guy here, and here, and here, and here. Yeah, this looks super ugly actually. Not very happy with the look of this, but maybe we can make it work. Here we can take this maybe unused away and replace it with this random function instead, because we're gonna need the rand. Because the rand is used here. All right. Yeah, maybe you can close your eyes for like 20 seconds and let me just do this, because this is so ugly that I wouldn't really wish this on my worst enemies. Yeah, then we have the Y fragment. It'll be interesting to see if this actually generates the correct code. I think it should. It should do that, and it should do it. It does all of this nastiness now at code generation time, so that's nice. Never reaches the game. Right, that's the Z fragment. And then we have the W fragment, which is the last one. Min W, max W. Zig actually has a very nice syntax for this. In Zig you could do this, you could do this fragment, W fragment is if, and then, take those away. You could do this, and then put a semicolon there, but you can't do that in C#, fortunately. In C#, of course, we have the ternary thing. Maybe we should turn this into a ternary thing instead. So we could do like that, and then burp, and then it would be colon. Is this maybe slightly? Yeah. Can you please go away, light bulb? Bye bye. Thank you. Syntax is slightly different. Maybe that's nicer. I don't know. It's a bit more compact at least. Some of the ugliest code I've written in years, I must say. I want to do like a usability and beautification pass on this whole system at some point. To be able to do that though, I want to first of all profile that this actually gives me the speed up that I want. Otherwise this whole exercise is kind of pointless. It's not necessarily pointless, but it puts into question how widely this thing will be used. And second of all, I kind of don't exactly know what the best way to generate this kind of code is, other than doing it like this by hand. So I had a little bit of the same thing with the shader generation, which I did like five or so years ago, and I actually made it kind of nice in the end. So I'm thinking I can probably do that here as well. When I somewhat know what kind of code we need to generate, then it can be made nicer. Now it's just basically like hammering on it until it works. Most of these things. Okay. Cool. I think this is probably good. Let's see. Let's play with the node graph a little bit. So we go in here, and then what was the ID of that? It's number 13 actually. Node graph 13. Okay, so we can plug this into some other things. We can plug it into there, and we can see that the value nicely switches to point to node 39. And we can make this like a 2D vector. We can plug that into there. Yep, that looks good. That looks excellent. And if we switch that to, like, say 223, that works, and that can be 7, and it works, and that can be 3.141592, and it works. Cool. Yeah, I think we're done with that node. That horrible thing of a node. So now we have the vector operation, which should be kind of similar to the float operation, except that we're operating on vector variants instead. And a vector variant is kind of like my type here for. It's kind of like a union type. It can support anything from 1 to 4 dimension vectors and colors, things like that. And then we have the swizzle node. So they should be, the vector operation should hopefully be kind of simple. Let's look at the float operation. So we have essentially just like a mirror of this vector op node. Let's put this on the right side. I think we should have a quick look at it in the C++ code as well. So vector op node, and that looks like this. What is this? What is happening? Oh no. Oh no, this is horrible. Oh, right. Yeah, so what we're doing here is we're actually figuring out here at runtime, I should add that, how many components do we have? Because like I said, the variants can support any number of, well, not any number, but from 1 to 4 dimensions. So we're getting the minimum, and then we are actually calling like apply 2D. Yeah, the operation is here, and then 3D, and then 4D. Seems kind of convoluted, but maybe that's apply splat second onto first. If the second operand is 1D, we splat the value across the first operand's components. Yeah. Yeah, so that's so that we can do things like a vector 3 times 2. So that would be 2 vec variants, where the second one can be a 1D. Yeah, this is probably pretty good, but it's kind of annoying to write. Didn't remember we had this much crap here to deal with. Well, the good thing is that we can move all of this to be code generation time again. Stuff like this is like one reason why the interpreter is so slow, is that like it doesn't know what the data is beforehand, so it needs to deal with all of this crap at runtime. And of course the native code one knows all of that. But it knows most of it, it doesn't know all of it. It can't, for example, it can't really know the component count. Yeah, it can't know the component count at least easily. So this particular thing we might actually have to do at runtime. That's annoying. That's annoying. That's annoying. What do we use that for in this particular effect? Because I like to end this stream by doing some profiling. So let's see. Where do we have vector operation? Vector op. I have just a single vector op. It's node 26. Here we go. Okay, so we're just multiplying some color by some other value. Okay. Yeah, we're sort of modulating the color here. Okay. Yeah. And it's actually just a random float. Yeah. Okay. So yeah, it's these two operations that we still have to do. This vector operation node is a very important one, but I'm wondering if I can cut some corners here. And I probably actually can. So, okay, what I'm gonna do now is, because we only have one vector operation node and we only have one swizzle node, right? Because I'm kind of thinking that I might run out of time. Yeah, we have only one swizzle and we have only one vector operation. So what I'm gonna do is I'm gonna just hard code these operations that they do currently into those nodes so that we can get this thing into the game. And we can run it there, and then we can do some profiling on it, which is the interesting part. And then I'll figure out off stream how I want to do these nodes, and it's going to be completely representative because it's going to basically generate the same code, same operations, but we don't need to worry about different dimensions or anything, because we know this is a 4D vector because it's a color, and this swizzle operation here actually outputs a 4D vector xxxy, so it's fine. So it's going to be completely representative of what it will eventually, of the code that it will eventually generate for us. Yeah, here we actually have some like multiple curve. Look at like points equals. There's one curve node, number 17, and here's another one, number 20. Yeah. Already in heavy use, right after we generated it. Okay. I'm gonna just snap an image of this section I can have as a reference. And then we will do tire lat slip gravel. MRL effect, right? Sure. Export that out. The asset server will tell us that, yeah, it's up to date, okay? Whatever. We need to get the resource path to this to be able to actually use it in the game. So it's the bin MRL effect. Let's convert that, and then the long. Let's convert that, and the asset server will give us those two paths there. That's neat. So let's do the boilerplate stuff that we need to do here to actually be able to see these things in the game. So where did I put it? It was here. Move that off to the side. So we create one file which is called game Merlin effects material effects, and then it's tire long slip gravel.zig. So my thinking here is that I will actually generate these these names here based on their resource paths eventually. And then we need this small piece of header. So that's the lateral one. You can get that by just copying it out of there, and we need to hash it somehow, which we'll get to in a second. Add a 0 there to specify that it hasn't been done yet. Yeah, I have my hashing code here ready to go. So let's hash this one first. I will just call that lat hash. And then we do long hash. I need a better way to just hash strings on demand. And the tools can even do it, but I don't really have it exposed to the UI currently. And of course the system will do it for me when I get all of this build infrastructure in place. We're not quite there yet. So just go here, and then we go to here, and then we have lat hash and long hash. So let's copy those into the respective places. That was the lateral one. And these hashes are how the game actually identifies these node graphs in the DLL. It knows that, okay, I'm going to play a particle effect because you've told it the resource path to the particle effect, which of course you need if you are going to play back the interpreted one, because the interpretation or the interpreter data is found in that resource file with that path. But in the new version, if you have the native DLL containing the native node graphs, if you have it loaded, you can ask that thing, hey, do you have a node graph for me with the hash of this path? And you give it, for example, this thing, or the game hashes the path and gives it here. And so that's why we need to actually have, this thing is not actually even used here. I just keep it around because it's easy and nice to have it in place here as well. But this hash is how it actually identifies those two new node graphs now. So it knows which one you're actually requesting. Node graph 3 game. Let's do lateral. And then number 4 would be the longitudinal. Something like that. And I feel like I have to do this quite soon so that I don't lose my mind just doing this, generating this by hand all the time. But the nice thing, of course, is that you can have the game play both native and interpreted particle systems just fine. So you can have a few interpreted ones, and it's probably not going to be a big deal. There we go. Okay. Right, right, these two are now a different color because we don't actually have those kernels there yet. We're gonna have to generate the kernels for ourselves. So let's do that. I'm gonna basically just open one of them and copy that into both because they're essentially the same. And then we're gonna just handwrite the code for the swizzle and the node operation, vector operation. Let's go with the lateral one, it doesn't matter. And I'm gonna copy all of this, copy, and paste it into the lateral one and the longitudinal one. And we have some errors. Why do we have errors? Self. Oh, okay. Yeah. See, this is this is exactly the problem. We have the vector operation node and we have the swizzle node. We can just save it and it will auto fix it. That is perfectly expected because we haven't implemented those guys yet. So for the vector operation node, if we look here, the vector operation multiplies two values, one which comes from number 27, so vector op number 27, and another one which comes from 31. That would be the vector operation. However, the swizzle node is sort of higher up or comes before that, so we're gonna have to probably do this one first. 31 gets its value from 28. So we can do something like const value is self.kernel.node28 get result. So now we've read this bin. And then we need to output one which has the x coordinates splat across the three first components, and the second one should be 1 because this is xxx1. There we go. That's the swizzle node, and then the node 26 quite simply just multiplies those two together, so 27, 31. Value 1 is self kernel node 27 get result. Const value 2 is self kernel node 31 get result. And then what is multiply? Is it like a component-wise multiplication? Let's look at the C++ version of that. So vector op. Let me get back to this craziness. Right, it just runs probably. No, it's a component-wise multiplication. Yes, okay. It's a component-wise multiplication. Yep. So we do basically. Well, that's supposed to be a 4-dimensional vector. So do value 1.x times value 2.x. Let me do this 4 times. W, and that's it. That's everything. And now we need to take all of this stuff and we actually copy paste it into this other one. Now that we have the correct. Yeah. Cool. Oh, component-wise random vector node, this can't actually be const. Yeah, that makes sense. Yeah, we need to change that actually. Yeah, now it builds. So the component-wise, that's not it. It's actually here. Let's shut down Merlin. Nope. Component-wise random vector node. And needs to be a mutable pointer. Which is a little silly, but whatever. It changes one of its members, one of its fields. So I guess it makes sense. Cool. Now then. That should be it, really. Let's run the game. See what's what. And maybe we should make it. Maybe we should make some very obvious change to that to make sure that we are actually running native code here. Let's do like longitudinal slip, which I think is the more common one. And do color. Find the color node. Particle color node. Color vector node. That's what I was thinking. Yeah. So let's return here like a red color, right? So 1, 0, 0, 1. Well, it should be 0.0, I guess. So now they should be clearly red. Let's see if they are. They are not. Did I put it into the lateral one, perhaps? No, looks like it is in the longitudinal one. Yep. Is there some other place in the code that kind of mixes those up? I wouldn't put that past myself. Let's build that. I guess they might be just like flipped around or something. It's entirely possible. I don't think so though. Okay, they're like clearly not getting red. So why are they not getting red? Does that mean that we are not actually running? We just put a print here. Sprinter print getting color. Something like that. Let's print the time here as well. Yeah, like that, and then do self kernel. Effect time, I think it is. Self, right? We don't have a self there. So that would be the lateral one. And then the longitudinal one would be this. Long. what's it called? Time. Node graph time is what it's called actually, yeah. Not effect time. Okay, do we see those outputs then? Or what's going on? Yeah, we're clearly not running that particular effect with from that one. Okay, did I just quite simply miss some of the places? Yes, I did. Oh, stupid. I missed arguably the most important one, which is like, do you have this particular node graph, Mr. DLL? Well, that makes perfect sense, and that also shows that my detection logic is working. So now we should just see like a whole bunch of outputs. Oh, unimplemented billboard particle renderer. Ah, what? What? Berlin billboard particle renderer. Oh, okay. Okay, we need to do that as well. Okay. So, mesh particle renderer, this one. Let's put that to the side. This guy implements the new structure of arrays rendering method. The billboard particle renderer does not, but we basically just need to I think copy this over. That should be exactly the same. Update. So update, put it there. What's B? SOA particle bucket. Yeah, we need that. We need that type. These two renderer classes are in many ways just like mirrors of each other. We need to add an add SOA particle to batch function. We need to add that to the Merlin. So when I added support for well, all of this essentially, all of this native particle business, I also changed the way that particles are represented in memory so that we can more easily poke at them in a performant way from the DLL to the game, or from the game to the DLL, and basically that means that for the time being we have two systems. We have one which uses the old particle struct, which looks like this, and it's an array of structs, and the new system uses a struct of arrays instead, which is typically considered to be a bit faster. Right. So here we need to do this instead. We don't have a P. We have a bucket color. So we should be able to do that and that. Color or paint map rect. Yeah, that looks good. That's that. Then we have P rotation. So that would be bucket rotation index. Like so. And we have scale. That's bucket scale index. And position is there. And is that it? Oh, there's something more. There's scale there as well. There we go. Then we have position, yeah. There we go. That should be it. So now I think we should have support for billboard rendering with native node graphs. And look at that. Now we have red. Now we have red little things coming off the wheels, just like we expected. Excellent. We should have a lot of those outputs as well. Yeah. Getting color. It's getting color. You can see that many of those are very, very short-lived because it's getting the time. It's printing the time. The time is like, well, we have a few. There's one that was like 2.5 seconds long, but many of them are like just like sub-0 seconds long. Okay, excellent, good. That means that we can now undo all of this funky business that we did here. All of the funky business. Like so. Same thing here. And there we go. So, okay, excellent. There's barely anyone in the stream. Can't be helped. I blame the time of day again. I refuse to believe this is not interesting. But I, however, consider this a resounding success because we now have all of the particle effects for these vehicles running as native. And now we come to the interesting part where we actually profile the update for these vehicles. This is the thing that I've been sort of waiting for well, about a week now, doing this business. Like, is it actually worth doing? Is it actually going to be faster? I don't know. We're going to figure out right now. What is this actually printing? It's printing particle effect being released, yeah. Or native particle effect being released. It is coming from the effect instance. And it's this thing. Let's get rid of that. Like so. And so, right, we're gonna end this stream with a little bit of profiling. And the way I'm gonna do that is I'm gonna quite simply just not load that DLL, which means that we will be running with interpreted particle systems. And then there's not going to be like a super scientific profiling because you would really need to have some sort of like choreographed movement that like a bunch of vehicles are doing to get that. But I will just like play around a little bit and have some other vehicles driving here and see what's happening. Also worth keeping in mind that like this smoke pillar here is still running. This is the most complicated one by far and it's still running in interpreted mode, so that's something to keep in mind. We will see that as sort of like a baseline always. Anyway, let's start with some interpreted mode stuff. I can go to Merlin Manager and comment out my natively define. So now we're falling back to the interpreted ones. I'm gonna get the profiler up. It's running here on my second monitor so that I can actually see the game. Maybe I should run the game without the debugger actually. Right, so it looks like this. Here we have Merlin effect description, update instances, effect instance update, something like that. 0.4 milliseconds now. That's basically just that smoke pillar, I bet, taking like half a millisecond or something. I don't think we have any other effects, but we might. I don't know. But yeah, we're never gonna get lower than this currently until I have that ported to native as well. But anyway, let's keep that running in the background. I'm gonna bring in some other vehicles here. Load test vehicles. Load test vehicles. Then we're gonna do the same thing, both with native and with interpreter. Well, I'm gonna drive to a remote part of the map, and then I'm gonna ask those guys to come to me so that we have some vehicles driving and causing particle effects to be spawned. Right, just drive into this wall here. Boom, and then we go. Okay, move here, move here, move here. Now we can just take this thing and see what is happening here. So here's the stuff that happened while I was driving. We can see some slight increase here in the time. All right. Yeah, we're getting some readings. I'm going to move that off to the side, and we're going to see those guys should arrive pretty soon. And we have one arriving already. So there should be three guys arriving. And yeah, we can see that like starts going down immediately when these guys are slowing down. So now we have just the one river truck arriving like a drunk driver. Okay, so here's the result of that. Let's stop the profiler, disconnect the monitor server completely. And here we go. So this is the interpreted run. I'm gonna move that off to the side, and we're gonna re-enable the thing. And again, I ran it with the debugger, but whatever. Let's stop that. Stop it. Run it without. Let's start another one. Alrighty then. So let's do the same thing. Load test vehicles. I'm just gonna drive. So move here, and move here, and let's see what is happening here. Okay, yeah, we do actually have quite a few spikes going on. The nice thing, of course, here with this is that we can actually profile. We can add like profile blocks. So if we have like 1 or 2 nodes that are particularly heavy, we can see what's going on and reason about it in a more interesting way than before. Well, technically, I guess we could probably have done that at least for the nodes with the interpreted one as well. Okay. So that's one guy arriving. Yeah, there's clearly some optimization still to be done here, because this is not like a whole lot better than we had. You see that like on average we're sitting at about 1.5 milliseconds. And it's actually like even a bit lower here. This is very surprising. Very surprising. But okay, now we have some data to work with. So a few things come to mind here that I might want to try. First of all, it is possible that the jumping between the EXE and the DLL is causing some of this slowness. Because we're going through like function pointers. And if that is the case, then I actually already have a solution, proposed solution for that, in which we would like batch update things. So batch update all of the effects for a given all of the instances of a given effect, essentially, by going like once over the boundary. That shouldn't be super difficult to do. And then some of these are clearly like there's clearly something that's very, very, you know, very heavy here, which we are going to want to actually track. So yeah, that's a little bit of a disappointment, I must say. Of course, we do have that big one still running in the background. Would perhaps be interesting to just like turn it off, which I can't easily do right now, but it could be done from the level editor. Just turning off this guy. Another thing that could be worth looking into is that if there's some overhead there on the like outside of the node graph, but still inside. Let's see, advanced time. See, which one is that? Yeah, this is the interpreted, and this is the native one. Let's put this side by side here. Okay. Okay, so now we can clearly see. Now we can clearly see some differences here. We can see that with the native one, the update of the node graph, which is of course exactly what we have been working on here, stays at a pretty fixed 0.4. There's some spikes every now and then for some reason, but it stays at a pretty fixed. So this is the Zig code running advanced time Sprinter node graph update. Here the node graph update is more sporadic. So this is nice. This is positive. I think, and I probably need to verify this, but I think this is where they all started driving together, so that they were like causing lots of particles to be spawned. This is where I was driving to that place, and then this is where I asked them to come to me. You can sort of see the same thing here, but the actual node graph update is very flat. Cool. So this is encouraging. It just tells me that there's some other business going on inside of effect instance update that I need to, or actually rather advanced time, that I need to look at. Here that thing is taken up basically entirely by the node graph update. You can see they're essentially sitting on top of each other. Now here it is no longer the case. So what else do we have inside effect instance advanced time? Because this is cool. 0.4 milliseconds. Could be better, but it's not bad. Let's have a look. Effect instance advance time. Yeah, there's really kind of nothing. There's really kind of nothing. Oh no, you know what this is? You know what this is actually? Now I realize what this is. This node graph thing is actually a call to this, which means that it has fallen away from isNative and into this else. So this is not actually the sync code. This is the smoke pillar, which is such a ridiculously heavy effect that just one effect takes, about half a millisecond. Yeah, okay. Okay, that's why it's somewhat flat, because it's somewhat uniform, right? So okay, that still means that the rest of this is actually the sync code. So this is the sync code here. So we can sort of like subtract, one from the other, and we get the result. So yeah, there's a little bit of more performance investigation to be done here, but still, like, this is now we have some data that we can work with. We can figure out, okay, where are the slow paths, where are the hot paths, all of that. So pretty cool. Performance needs some work still, and obviously there's still work with the actual code generation and everything, but it does work. That's the most important part right now. It does work, it looks correct, it behaves correctly. Now we can try to figure out, do we have any slow nodes? Do we have any particularly slow nodes going on? And do we have some, like, just generic optimizations that we can do, like batching updates, things like that. But that's cool. I think I am done for today. I have been doing this now for 3.5 hours. It's been a pretty slow stream, which was to be expected, but I got some pretty good work done, and this thing will be available in VOD form anyway, so I kind of expect that to be the place where most people actually find this thing. As always, remember to like, subscribe, do all the YouTube jazz. If you want to help out the project, do check out the link that I put there in the chat in the beginning, and go wishlist the game on Steam. It helps out tremendously. If you want to ask questions or be more involved in the development and play Pre-Alpha 3 as soon as it launches, which will be relatively soon, hopefully very soon, then do join the Discord. There's a link in the chat for that as well. Other than that, have an excellent rest of your day. Take care, and I'll see you next time.